Hello everyone, welcome to HUB360 Embedded Sphere, to the world of embedded system, the invisible tech powering our smart world. At HUB360, we are not just selling components, we are unlocking creativity and innovation. This tutorial is your first step into building devices that do more and think smarter. In today's video, we are building an RGB color switcher using an Arduino UNO. With just a single button, we'll cycle through different LED colors, and after the fifth press, the LED turns off. So here are the components we'll be needing. One Arduino UNO, a jumper wires, RGB LED, a tact switch button, and our breadboard. Okay, let's connect our RGB to our breadboard. We are connecting the RGB to the breadboard, and the longer wire, which is our ground for the common card, since this is a common cathode, will be connected to the negative rail of the breadboard. Then for our red LED, our red color, we are connecting it to digital pin 3 of the Arduino. 0, 1, 2, 3. Then for our blue LED, we are connecting it to digital pin 5. Then for our green LED, we are connecting it to digital pin 6. Okay, now let's connect our tactical switch. Remember I said for your tactical switch, when pressed it is high and when released it is low. So we connect our tactical switch this way, and for our tactical switch we'll do it in such a way that it is more like a pull down, where we connect one leg of the tactical switch to ground, that's the negative rail of our breadboard, and the other leg to pin 2. Okay, now let us connect it to our system. Let's break down the code that controls our RGB color switcher system. Pin definition, we have int red pin equals to 3, green pin 5, blue pin 6, tact pin 2. First, we define the pin numbers for the 3 color channels of the RGB LED and the button. We are using pin 3, 5, and 6 because they are PWM enabled. This is important because we will use analog write to control the brightness of each color, not just on and off. So we go to the button states and press tracking. We have int last button state equals to 1. So we define some variables to handle the button press logic. Last button state stores the previous state of the button so we can detect transition. Current button state stores the states on the loop iteration. Press counts keeps track of how many times the button has been pressed. Max presses is the threshold we use to turn off the LED and reset the circle. Note, the button is wired to ground and we are using input pull-up. So when the button is not pressed, the input reads high, and when pressed, it reads low. So we go to the setup function. In the setup function, we begin with serial communication at baud rate of 9600 to monitor debug messages. We then configure the red, green, and blue pins of the RGB as outputs. This allows us to control the brightness of the red, green, and blue channels using PWM signals. Here we configure the tactile button pin as an input pull-up. This enables Arduino internal pull-up resistor, which means the pin is held high by default. When the button is pressed, it connects the pin to ground, making it low. This is very common and reliable method to handle button input without needing an external resistor. Then we go to the random seed, analog read 0. This line is used to initialize the random number generator with a more unpredictable seed. We are reading from analog pin A0, which is left floating, meaning it's not connected to anything. A floating analog pin tends to pick up random electrical noise, giving us a slightly different value each time the Arduino resets. That makes our random LED colors more truly random every time the board powers up or resets. This is more effective than using a fixed random number like, say, random seed 1, 2, 3, 4, which would produce the same sequence every time. Then we go to our main loop. Current button state is equals to digital read tact pin. Inside the loop, we read the current state of the button. Since we are using a pull-up configuration, a press button returns low, and we see if last button state is equals to 1 and current button state is equals to 0. Here we are checking for a transition. Okay, we go to the void loop. Inside the loop, we read the current state of the button. Since we are using a pull-up configuration, a press button returns low. So we say current button state is equals to digital read tact pin. And we say if last button state is equals to 1 and current button state is equals to 0. Here we are checking for a transition from high to low, which means the button has been pressed and then released. Without this check, the loop would keep detecting the button as pressed as long as it held down, preventing us from using it for single press and release action. Then we have press count plus plus. We increment the press count by 1. This keeps track of how many times the user has pressed the button in this circle. Then we go to the if press count is less than or equals to max presses. If press count is less than or equals to max presses, int red value is equals to random 0256. So that place, it means if the press count is less than or equal to 5, we generate 3 random numbers between 0 and 255. This represents the intensity of red, green, and blue. Using analog write on PWM pin, we mix these colors to produce a wide range of RGB combination. So for our PWM, which means pulse width modulation, allow us to control brightness by rapidly turning the LED on and off at different duty cycles. Then we go to if press count is equal to max press. When the button is pressed for the 5th time, we turn all color channels off by setting their PWM value to 0. We also print a message to the serial monitor for debugging. Then the line 43, we go to if press count is greater than or equals to max presses. After the LED is turned off, we reset the press count to 0 so the color cycling can start over on the next press. Then we have delay 200, debouncing with delay. The delay 200 adds a short pause, 200 milliseconds, to help with debouncing. Mechanical switch like our tact button can bounce rapidly when pressed, causing multiple unintended triggers. This delay ensures the code doesn't register a single press as multiple ones. Then we have in line 51, last button state is equals to current button state. At the end of the loop, we store the current state into last button state so we can check for the next change on the following loop circle. And that's how the code works. It checks for when the tactical switch has been pressed, uses PWM to mix color, and adds random values to keep it interesting. After the tact switch is pressed 5 times, it powers down the LED and resets the count. It's a great demonstration of digital input, output control, and simple state management using Arduino. Now that we've gone through the code and understand how it works, it's time to upload it to the Arduino. Connect your Arduino UNO to your computer using a USB cable. Open the Arduino IDE and paste in the code. Make sure the correct board and port are selected, then hit the upload button. Once the code is uploaded, keep the RGB connected and test the project. Press the button a few times and watch as the RGB LED changes color. On the fifth press, the LED should turn off, just like we program. If everything works as expected, we can now power the project without the computer. Okay, this is a great beginner project to help you understand how digital input and output work with Arduino. You can find the components used in this project along with a link to the HUB360 website where you can purchase them in the description box below. The complete code and freezing circuit diagram are also available there to guide you step by step. Thanks for watching. If you enjoyed this project, make sure to leave a like and don't forget to subscribe for more electronics and coding tutorials.